In this video, we will be talking about product and quotient rules for derivatives, as well as thinking about derivatives just a little bit abstractly, and maybe one other topic to be determined. So here in the first portion, we want to talk about the quotient rule and product rule for derivatives. And before we even get into what those are, I want to recall your knowledge of functions. And normally when you first learn about functions, you learn about notation. And so with derivatives, we learned about some notation. Then with the functions, you learn how to add and subtract functions to and from each other. And in derivatives, we've already done that using the sum and difference rule, right? I said you don't have to prove those steps. We are just going to use the sum and difference rule, but we've already talked about the sum and difference rule. And then when you talk about functions, you then switch over from adding and subtracting functions right into multiplying and dividing functions. So this is following a pretty standard route through mathematics, except now we're looking at the product and quotient rules for derivatives, talking about calculus now. So we let u and v be functions in terms of x. So just for example, u could be equal to x squared and v could be equal to x cubed minus x. So these will be expressions in terms of x here and here. So if you have the derivative of two things being multiplied, you'll use the product rule. And how I say it, the derivative will be the first times the derivative of the second plus the second times the derivative of the first. And you can say the exact same thing over here. You can choose to use the prime notation or the dx notation. I will tend to use this notation here, but if you use this one, it is exactly the same thing. And so there's the product rule. And in the quotient rule, you can see that clearly that we have the quotient of two different things, and we're trying to find the derivative of that. You have the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared. And it's the same formula over here, just in ddx notation. So I will, again, use this in examples, but if you are more comfortable with prime notation, feel free to use that. A couple other things I want to mention to you here is that when you're using the quotient rule, it is important to have everything in this correct order. You will start and end with the denominator. And another way you can say this is you can say that this is low d high minus high d low. And I heard this from a college buddy of mine, low d high minus high d low. He said it worked wonders in his brain, so maybe just another way you can keep it straight in your head. Low meaning the bottom, d meaning derivative, high meaning top. So low d high, bottom times the derivative of the top, minus high, top, d low, derivative of the bottom. And then you'll just have to remember over low squared or something. Let's take a look at some examples using these rules. So here we have a couple of examples, one using the product rule and one using the quotient rule. And you can tell just by looking that since this is a function times another function, that this will use the product rule, and clearly because there's a fraction here, that since there's this fraction, this will use the quotient rule. So up here at the top, what I want to do first is call my two different functions. Like I know the first part is x squared, and the second part of this is cosine x. So what I will write over here is that the derivative f prime of x will be the first times the derivative of the second. And I'm actually going to write this out, d dx cosine of x plus the second function, cosine of x, times the derivative of the first function. So here we go. This is not even calculus yet. We haven't taken any derivatives. So the first step is to just get everything set up. So first, which is x squared times derivative of the second, cosine x, plus the second times the derivative of the first. Well, then the calculus part is to actually take these derivatives. So the answer will be x squared times the derivative of cosine x is negative sine of x plus the cosine of x times the derivative of x squared is 2x by the power rule. So then I'm just going to rearrange a little bit of this. So I'm going to move this negative to the front and just call it negative x squared sine of x plus, and I'm going to move this 2x here to the front of the cosine x to call it 2x cosine x. And there's my answer for two functions that are being multiplied together, x squared and cosine x. This is what the derivative is down here. Now for this second example, I mentioned earlier that you can see that since there's this fraction, we will be using the quotient rule. And how I'm going to write this out is g prime of x equals low, which is this function here, 3 times sine x, so 3 sine x, d high, so the derivative of x to the 6th plus 5x, and again I'm going to write this derivative out like this, d dx of what's in the top, minus high, so x to the 6th plus 5x, d low, so the derivative of what's in the bottom, 3 sine x, over 3 sine x squared. There we go. And then the only thing we have left to do now is to actually take the derivative of each of these little pieces here, and we will get our answer. And so you can see down here with this answer that the derivative of x to the 6th is 6x to the 5th, the derivative of 5x is 5, and the derivative of 3 sine x is 3 cosine x. And just for fun, I squared the denominator. We normally won't do that. You'll just normally want to leave it squared. But I wanted to make sure you all understood that 3 squared is 9 and that sine squared is sine squared. So that square affects the 3 and the sine of x. On to some more examples. On this slide, there are two examples. You see that there's an example f of x equals tangent x and g of x equals cosecant x. So yes, while there hasn't been too much trig in this course so far, we're about to get into it pretty deeply. So hold on, everybody. You may know that the tangent of x, we haven't talked about a derivative for that yet. But we can figure out what it is if you recall that tangent can be rewritten as sine of x over cosine of x. Well, now this creates a quotient, which means we should use the quotient rule here to figure out what the derivative of tangent of x is. So with this quotient rule, we can call the sine of x the top function, and the cosine of x the bottom function. So remember, you always start and end with the denominator. So f prime of x will be the cosine of x times the derivative of the sine of x minus sine of x times the derivative of cosine of x. I'm going to go back here and put in my brackets. There we go. And all of this will be divided by cosine of x squared. So what do we need to do here? We need to make sure that we can take the derivatives here of the sine of x and the cosine of x. So what this will end up giving you is cosine squared of x plus sine squared of x over cosine squared of x. And that's because when you take the derivative of sine of x, you get a cosine x. Cosine x times cosine x is cosine squared x. And the derivative of cosine x is negative sine x. And since this would be a negative sine of x times a sine of x, but you're subtracting that, you'd end up with a positive sine squared x. From here, you can rewrite this as 1 over cosine squared x, and that is because of the Pythagorean identity, the one that everybody remembers, sine squared plus cosine squared equals 1. And then from here, because we can simplify this trig function just a little bit more, 1 over cosine x is secant x. So if you have 1 over cosine squared x, that leaves you with a secant squared x. So now you can state fact that when you're trying to find the derivative of tangent of x, the derivative is secant squared x. And you can go through a similar process with the cosecant of x down here when you rewrite it as 1 over sine of x and you use the quotient rule here. That ends up giving you this if you apply the quotient rule with the start and end with the denominator. So start with the sine of x times the derivative of the top 1 minus 1 times the derivative of sine x over sine squared x. Now the cool thing about this is that the derivative of 1 is 0. And if you multiply sine of x times 0, that just means this whole first term ends up being 0. So we only have to really worry about this derivative back here. The derivative of sine is cosine x, so we will have a negative cosine of x all over sine squared x. And to manipulate this to meet some trigonometric standards, we can rewrite this as negative 1 over sine x. So we peel off 1 sine x from this here. And to that, we multiply another fraction that is cosine of x over sine of x. So 1 over sine x, we already talked about that. 1 over sine x is cosecant x. So negative cosecant x, the negative is right here, times cosine over sine is not tangent. Cosine over sine is cotangent. x. So now we can say that the derivative of cosecant x is negative cosecant cotangent x. And the rest of the trig rules follow on the next page. Here are the rest of the trig functions you knew sine and cosine coming into this lesson. In this lesson here, you can see that we take the rest of the trig functions, tangent, secant, cotangent, cosecant. And now that you know the quotient rule, you can go back and prove these other two if you desire, just by using the quotient rule and setting up secant as 1 over cosine and setting up cotangent as cosine over sine. But these are rules that you will want to memorize. It'll just make your calculus life a hell of a lot easier. That being said, with the previous two examples of derivatives, you notice that there wasn't too much simplification that was happening. And that is because I have not given you some simplification rules for derivatives. And that means when you see these words, find the derivative and simplify, there are some rules that you should follow. The first one being common factor if possible. If you can common factor something out of all of the terms, do it. If you forget to, it won't be too detrimental, but at some point it will make the final answer much more comprehensible. Another rule that you want to follow is that if there is in fact a fraction, one fraction, any fraction within your derivative and you're directed to simplify, you want only one fraction. Everything's got to be in a fraction. So for example, if you have like 1/2 plus 1 over x is what you get from your derivative, then you need to combine it into one fraction. Or something like this, if you have a fraction within a fraction, then you can only, simplified means you only have one fraction. And you can even have something like this. If you have x plus 1 over x, and it says simplify, then you need to combine this into x squared plus 1 over x. So if there's a fraction anywhere, you need to make sure that your answer, your final answer, is completely just one fraction. The last thing that I can think of for right now anyway is if you have any bit of cancellation that can happen, then you need to make that happen, as that is part of simplification. So if you common factor and you're able to cancel anything in the top and bottom after that, then do that. Or if you notice, like when we were doing limits of derivatives, the +2 and the -2 in the numerator cancel out, cancel those out, just to make your life a heck of a lot easier. Those are the simplification rules for me for now. I might think of one more a little bit later, but when I do, I will let you all know. Differentiate and simplify. If you take a look at example 1, you can see that the product rule will be used because we have this function, x to the 3/4 times this function, 6 minus x. And so f prime of x equals the first, which is x to the 3/4 times the derivative of the second, which would be 6 minus x, plus the second 6 minus x times the derivative of the first, which would be x to the 3/4. Now all we have to do is take the derivatives of these two here to get a derivative of x to the 3/4 times -1 by the power rule in this part here, plus 6 minus x times 3/4 times 1 over x to the 1/4. And that is because, the 3/4 is pretty easy to understand. You just bring the exponent to the front. There it is, 3/4. But when you subtract 1 from this exponent, you get x to the -1/4 power, and the -1/4 power tells you to write that variable in the denominator with a positive power. So one more rewrite over here. I'm going to write -x to the 3/4 power plus 6 minus x times 3 over 4x to the 1/4 power. All right, that's not so bad. That's a derivative, but that's not the simplest version of the derivative. The simplify word tells us that since there's a fraction here, we must also have this fraction, this be a part of this fraction. So we want to write this as one fraction. So I'm going to start this simplification down here in purple. I'm going to separate these two problems first. There we go. So in purple down here, this would equal, since the denominator is 4x to the 1/4 power, this term also needs to have a 4x to the 1/4 power. So when you multiply top and bottom of this term by 4x to the 1/4 over 4x to the 1/4 power, that will leave you with this. You'll have -4x over 4x to the 1/4 plus 3 times 6 minus x over 4x to the 1/4. So now these two fractions can be combined into -4x plus, and I'm going to distribute this out, 18 minus 3x all over 4x to the 1/4 power. And this then becomes -7x plus 18 all over 4x to the 1/4 power. So there is a simplified derivative. This last answer over here in pink is a derivative, fine, but this is the simplified derivative, all in one fraction. Anything common factored out in the top, there's nothing to common factor, so we just leave it there. Cool, all right. So there's that derivative. Let's take a look at the second example. The second example, you see that we have g of x equals x times cosine x times secant x. Now, the product rule, as you all know and love by this point, only covers when two functions are being multiplied. There's another way to write this when you have three functions being multiplied. If you have f of x times g of x times h of x, the derivative of that is equal to the first and the second times the derivative of the third plus the first times the derivative of the second times the third plus the derivative of the first times the second times the third. So you can see that everything here is what I call a positive operation. We're adding, and then it's just f, g, and h all three times, f, g, and h, f, g, and h. But in the first one, you take the derivative of the last, and the second one, you take the derivative of the middle, and then the third one, you take the derivative of the first. So keeping that in mind, here is one function, here is another function, here is another function. And so when you go through and do this entire process, you can see that g prime of x will be the first, let me color code this here, the first and the second times the derivative of the third. And the derivative of secant is secant x tangent x. And to that we are going to add the first times the derivative of the second, and the derivative of cosecant is negative cosecant cotangent x, cotangent x, there we go, times the third secant x, plus the derivative of the first, which is 1, times cosecant x times secant x. And that's fine, and that's a really good derivative. But again, we have this direction over here to simplify. So again, simplifying, pull out common factors if you can, create one fraction if you can, simplify anything after that. So it looks like in all three terms down here, there seems to be a cosecant, cosecant, cosecant. Okay, so we need to common factor out a cosecant. Also, in all three terms, there is a secant. So we need to factor out a cosecant and a secant. So this will equal cosecant x, secant x. And what will we have left over? Well, if we get rid of the cosecant and secant here, we're left with x tangent x. If we get rid of the cosecant and secant here, that means we're left with a minus x cotangent x. And if we get rid of the cosecant and secant here, we're just left with the plus 1. So here's an example, another example of differentiating and simplifying the derivative. And one more thing before I leave this slide is that you notice over here in this first example, we used the product rule. Sometimes it might be easier to distribute one term over a couple of terms like this and call that equal to 6x to the 3/4 minus x to the 7/4, and find the derivative of this instead of using the product rule over here. But you will still have to simplify this answer and get something similar to what you see down here. So in the previous examples, we've been talking about the product rule, the quotient rule, simplifying things. Cool. Well, now I want to take it a step back to see how these derivatives work in a bit of an abstract way. Consider the following information. Suppose u and v are functions of x that are differentiable at x equals -3, and u of -3 equals -4, u prime at -3 is 2, v of -3 is 6, and v prime of -3 is 5. What you will be asked to do is to find the derivatives of u times v, the derivative of u divided by v, and the derivative of 5v minus 6u. All of these at x equals 3. So what you'll do for each of these is you will find the derivative of each using the rules. Like, for example, if you have d dx of u times v, that means you'll have the first times the derivative of the second plus the second times the derivative of the first. And all of this is happening at x equals 3. Sorry, -3. That being the case, now we can just look. This u at -3 is right here at -4. So this first one would be -4. This next one, v prime at x equals -3, is over here. So we would substitute a 5 in for that. So times 5 plus, over here, this v at -3 is a +6. So 6, that's like this. And then this u is u prime at -3, x equals -3 is 2. So we're just substituting a bunch of numbers in here. And what we're doing essentially is we're finding the slope of the tangent line because we will have a numeric answer. So when you simplify all of this down, you'll end up with -8. And you can do the same thing for the second example. That is d dx of u over v. So that means you'll set up the quotient rule derivative. So you start and end with the denominator. So minus u v prime all over v squared. And you're just going to substitute those numbers in. Like over here, v when x equals -3 is 6. So that will be 6. U prime at -3 is 2. So you can see what will end up happening here. This will be minus -4 times v prime at -3 is +5. So let me put parentheses around these, over v at -3 squared is 6 squared. So that leaves you with, let's see, 12 plus 20, because negative times negative makes a positive. 12 plus 20 is 32 over 36. You can divide both of those by 4 and get 8 over 9. And again, you can do the same thing with the last example, d dx of 5v minus 6u, and get, this would be 5v prime because of the constant multiple rule. If you're taking the derivative of 5v, well, you can just take the derivative of v and then multiply it by 5. So that would be that minus 6u prime. And that equals, let's see, v prime at -3 is 5, so this is 5 times 5, minus 6 times u prime at -3 is 2. So this gives you 13.